All right, hello everyone. Hi. I'm Zainab. I'm a functional programming trainer, and I'm really interested in the way that people think. And in particular, I'm interested in how we think about concurrency. So, first of all, I have a question for all of you guys. Has anybody had a bug in their code that only happens once in 100,000 times? Yep, a few. Okay, how about some, it only happens on CI, never locally? Yep, okay. You think it may be happening in production? Yep. A few of us have been there. For the ones who haven't, you'll get there eventually. What we've found is a species of concurrency bug. They are very hard to spot. They are even more difficult to test, perhaps even impossible to test, and they're also very, very hard to fix without introducing more concurrency bugs. Now, you might think that, well, we're using Rust, right? We have so much type safety, but types don't really help us when we're dealing with concurrency. We have really great tools for testing, but they don't really help us either. We can't really test concurrency bugs. Thankfully, we do have something. We have async programming. And async programming is a way of designing our programs and also a way of thinking that can protect us from concurrency bugs. So in this talk, I'm going to show you how. We're first going to have a look at async programming and how we can write code with it. We're then going to have a look at a few concurrency bugs. We're going to see if we can spot them. And then finally, we may have some solutions. But first of all, what is concurrency? Well, here are a few examples. For instance, you might be writing an application that serves HTTP requests, and you want to serve many requests all at the same time. You might want to query a database at the same time as serving those HTTP requests. Let's say that you have a game. You're going to have some kind of a render loop that's going to happen at the same time as your input loop. And even if you don't have that, even if you have something like an embedded system in which you think, oh, only one thing is happening at once, you'll still have something like an event loop in which you'll be receiving events at the same time as doing other things. So we're going to walk through our own toy example of a concurrency problem. We're going to cook breakfast. Now, I haven't had breakfast today, so I'm actually quite hungry. And this picture is very tempting. Here's what we're going to do. We're going to crack some eggs and then fry them. And meanwhile, we're going to fry some bacon for 5 minutes or until it's crispy. Sometimes, you can buy fairly bad packs of bacon. They'll never crisp up, but they'll definitely be done after 5 minutes. And it's important that we do all of these things at the same time, because otherwise our breakfast is going to be cold, right? But to start with, if we don't know anything about async Rust, maybe we could try this sequentially, just to get a feel of this problem. So first of all, our breakfast function, it cooks some eggs and fries some bacon. To cook eggs, we crack them and fry them. And in each of these functions, crack eggs, fry eggs, and fry bacon, we're going to just print. So we're going to print and sleep and print again. And our sleep is just a random amount of time. OK, that's what this synchronous code looks like. And this is the output. It's what we expect, right? We crack the egg, we finish cracking it, we then fry our egg, and then we fry our bacon. Now let's introduce some async. So you introduce async with async await, these two keywords. Let's play around with them. First of all, before each function, we write the async keyword. And whenever we want to do something with the result of this function, we call await. But if I run this, I get the same output, right? So what have I actually done? Aside from making my code more verbose, possibly less performant, why should I even use these async await keywords? Well, what I have done is that I've made a bit more explicit as to how I'm thinking about this code. I've explicitly stated that there is a sequential dependency of one thing on another. So if you have a look at our breakfast function, it's got a sequential dependency on cook eggs and fry bacon. Each of those things can also be composed of other things which are also in sequence. For instance, cook eggs is composed of crack eggs and fry eggs. And if we zoom into crack eggs, we'll see that that's also composed of some other blocks of started, are asleep, and are finished. So if we do this, if we think of our code in terms of blocks that we're composing, we can zoom into all of our blocks and assemble almost a timeline of events that happens, right? So first of all, we start cracking the egg, we finish cracking the egg, eventually we finish frying our bacon. Well, that's all very well and good, but this is just the same as our usual code, right? Why would we want to go to this effort of drawing such a diagram? Well, it's because we don't really want to do things sequentially. We want to do things concurrently. That's why, meanwhile, we're going to fry the bacon. And we do this with the join keyword, or primitive. So if we write join in our code, we can now cook eggs and fry bacon at the same time. And we can tell that by looking at the output. So we can start frying the bacon and start cracking the egg at the same time. We can express join in our code like this, or in our diagrams like this. We're going to put some boxes side by side to represent that we're doing them at the same time. And now, if we expand out these boxes into all of their individual blocks, we can assemble a timeline as well of cracking the eggs at the same time as cracking the bacon. Frying the bacon. Now, if you take a look at this timeline, you'll see that we're not actually doing things at the same time, are we? Or at least we're not actually doing things in parallel. But we are still doing them concurrently. By concurrency, what we mean is that we are interleaving these blocks in any order. And that can result in a different sequence of events. So the reason why concurrency is a problem is that if you think about it, if we're interleaving everything here in any possible order, there are many, many possible orders that things can happen in, and some of those orders can be very difficult to predict. We'll look at a few of those later. Well, there's another thing that we need to do. We've almost cooked our breakfast. We need to fry our bacon until it's crispy, or for 5 minutes. So this or until can be expressed with a primitive called select. And this is some pseudocode of what select looks like. It's a little bit like this. We're going to start a timer. That's going to last for 5 minutes. And we're going to crisp our bacon at the same time. If we look at the output of this code, you'll see that we start crisping the bacon, but we never finish it. Our timer finishes first. So with select, we can express that we want a particular relationship between these two things. We want one of them to finish first and the other to stop. Here's how we might draw that in boxes. We're going to have a timer box and a crisp box. And just as before, we can expand these, and we can interleave them. This time, however, as soon as we get to the end of one of our boxes, either finished the timer or finished crisping, we're going to stop. And we'll proceed to the next part of our program. So this is what our entire piece of code looks like, our example of cooking bacon. And indeed, if we do this, we will be able to cook bacon and eggs in a time that's quicker. So if you take this code, or this diagram, you can compose all these blocks. You can produce many, many different timelines. And you can have a look at all those timelines and try and identify, OK, which one is going to result in concurrency bugs. Are there any bugs? Can anyone spot any? No. Actually, there's no way for bugs to creep into the code that we have just written. Concurrency bugs creep into our code using very specific avenues. One of those is shared state. So let's introduce some state into our example. We're going to introduce a spoon. We're going to use a spoon to cook our eggs and crack them. And we're also going to use a spoon to fry our bacon. And let's imagine that we're in a really, really under-equipped kitchen, and we only have one spoon. We need to use that spoon among all of our tasks. Well, you might think, can't we just pass it in? Let's just pass a mutable reference to a spoon into our cook eggs and fry bacon functions. Surely this will work, right? But actually, no, it doesn't work and it shouldn't. So the Rust compiler is very helpful. It spots there's a mistake. We can't borrow mutably at the same time in two functions. So instead, we need to look into alternatives. One alternative to sharing state that we're going to look at is using mutexes. And this is just for demonstration. So let's say that we have a spoon mutex. We can do a few things with this. We can lock it, and we can drop it. Now, when we lock a mutex, what we're saying is that nothing else can lock that at the same time. Nothing else can use it until we actually drop. So what that means is that between the code here in which we lock and we drop, this function, cook eggs, is the only thing which is going to be using our spoon. This is how we might write our breakfast function. We can pass in that mutex, and everything here will compile. And we can run it. And if we run it, we'll find that one of our things is going to lock the mutex, in this case, the cooking eggs. And then only once that has been released is our fry bacon going to be able to get our spoon. There are no bugs in that either. Let's add some more state and see how they creep in. As well as a spoon, we're going to use a pan. Of course we use a pan, right? We use a pan to fry eggs and also fry bacon. And in our under-equipped kitchen, there's only one of those. Well, that's fine, right? We can just have another pan mutex, and we can go and lock that before our fry eggs function and drop it afterwards. And in our fry bacon function, we can try and lock the mutex. We might as well lock these at the same time, right? Why do we join here? Can anyone see a problem?
If the pan mutex is locked before the spoon mutex in the fry bacon FN, and meanwhile the spoon mutex gets locked within the cook eggs function, then you get a deadlock.
Yes, exactly. Now, that was actually a very long explanation, right? And those are all the steps that you need to have in your head when you're trying to debug it. Let's see if we can walk through it. So here's our output, first of all, just to demonstrate there is a problem. When we run this, we sometimes see that we can crack an egg, but nothing else happens. OK, let's expand all of our blocks to try and identify the problem. We see that if we lock the spoon in our cook eggs function, let's do that first. And then our fry bacon function locks our pan as our next step. What can our next step be? Well, cook eggs can't start locking our pan because fry bacon already has it, but also fry bacon can't go and lock the spoon because cook eggs has that. So we end up in this situation where we have two concurrent processes which are both trying to proceed, but actually can't get to their next step. And that means that neither of these can move forward. This is known as a deadlock. What you will see is that your application will just keep running but not do anything. Well, let's be a bit creative, right? Okay, so we've seen that this happens when we when we lock our spoon, but we don't lock our pan. So we had our deadlock. And now we're going to try and resolve it. Our deadlock occurred because one of our processes managed to lock the spoon, but not the pan. And the other process managed to lock the pan and not the spoon. So this time, let's just try and lock the spoon and try and lock the pan. And let's pattern match. And if we get both of them, that's all good. We're going to keep going. But if we only get one of them, let's drop the thing we have and just try again. And let's do this for both our functions, both our cook eggs and fry bacon. So we're going to loop in both of these, trying to get a spoon and a pan. And if I do that, I still see this. I don't get another step. But my laptop does start to heat up quite a bit. Sometimes, by the way, only sometimes. Okay, so let's try and walk through this and see if we can figure out what's happening. It's a bit more complicated now because we have loops. We need to try and think about loops, reason through loops in our code. Okay, so here's one thing that could happen. Our fry eggs function could lock our spoon. Then our fry bacon function could lock our pan. Then if this happens, then we can't exit our loop. We're going to keep going through. So then the next thing that our fry eggs function is going to do is that it's going to release the spoon. And fry bacon is going to release the pan. And it's going to try again now. There's nothing to say that the same thing won't happen, right? We can still end up in one possible timeline of events in which this just keeps and keeps and keeps looping. You might think, well, that's rare, right? That's not going to happen all the time. Actually, it's very, very common. And in some cases, depending on the examples that you have, how your code is compiled, it can be a lot more common than you'd expect. So this is known as a livelock. It is another concurrency bug. We've introduced it by trying to fix our deadlock, which was also a concurrency bug. So yes, I said, by the way, that async programming will help us, and I've shown you the different building blocks for it, right? Async, await, join, and select. And I kind of said, using these, we can resolve our concurrency bugs. But actually, we've just been able to find them, right? We found the bugs, but now what do we do with them? Unfortunately, there is no clear answer here. If you end up in these situations, you need to take a step back and think about re-engineering your code such that these bugs can be resolved, and that might mean making some trade-offs. So one of the things we could do here is that we could say that both the spoon and the pan, let's put that in the same mutex. This is a bit dissatisfying because if I told you that you needed a pan to crack an egg, you would look at me very strangely. But it does get around our concurrency bugs. Another thing we could look into, if we're going down this route, is to use actors. So who knows what an actor is? Who has a rough idea? Okay, fair few people. So I want you to imagine that you are a chef. You have a pan and a spoon, and you are inside a very, very dark kitchen. There are no windows, there are no doors. And there is a channel through the ceiling by which you get messages. And those messages are going to tell you what to cook. So you might get a message, for instance, that tells you to crack an egg. And if that happens, you'll take your spoon and you'll diligently crack your egg. And this is a bit like what an actor system is. You have all of these individual actors, perhaps a chef actor, perhaps another actor, and they can't communicate with each other in any way other than sending these messages. And these messages are always asynchronous, in that if you send a message, you don't actually really know that it's going to be received. And if you receive a message, you also don't reply to it synchronously. Now, you can send another message, perhaps to your original destination if you really wanted to. I like to think of actors like pneumatic tube systems. If you've ever been to one of those old hospitals and seen them, right? The way that you send messages to each other, or send pills sometimes around these hospitals is through pneumatic tubes. Now, this is what an actor might look like in code. We can create something called a channel. That's like our pipe for sending our message. And it's got two ends. It's got a sending end and a receiving end. The chef is going to take hold of the receiver, and that's what it's going to use to receive messages. And it's going to have its own internal state. It's going to have its own spoon and pan, and it never shares those with anyone else. So when it goes and it gets a message, that message is going to tell it to cook something, and it's going to proceed to cook. That might look something like this. Let's say it gets a crack eggs message. It's going to just go and crack its eggs just using the spoon. If it goes and is told to fry eggs or fry bacon, it's going to do those things as well. And it only ever does one thing at once, right? It only ever receives one message at once, processes it, and then it just sits and waits for the next one. So within an actor, everything happens, or at least these things are going to happen sequentially. Now note that we could still decide within each of these functions to do some concurrency. Well, how do we tell the actor to cook something? We take hold of the sending end of that channel, and we send it a message. So, for instance, we can send crack eggs, or we can send fry eggs. And we're going to do that in our cook eggs function. We're going to have another function, and it's going to send a fry bacon message. Now, we've got await here, implying that this is something asynchronous. Await does not mean that we are waiting until this message has been received. We're just waiting until it has been sent. And that means that this function is going to exit immediately before the actual frying of the bacon has happened. What we're trying to express here is that in sending a fried bacon message, we don't actually care really if the bacon has been fried. We don't care that it finishes frying. We're just instructing our actor to try and do it. So this is what our entire program might look like. We might have a join, so we can run all of these concurrently. And we're going to send our receiving end of a channel just to our chef, and take hold of the sender when cooking and frying. And we can express that like this. So we can have a chef cook eggs, fry bacon, and expand all of these out. And we can expand those out again, expand those out again, expand those out again, and then take that entire picture to build a timeline of events. And we'll see that sending and receiving need to be part of our timeline. A send always happens before a receive. So if we do this, we'll find that we will indeed be able to cook our eggs and fry our bacon, and everything will happen sequentially, but we only had one spoon and pan in the first place. So we've seen a lot of things. We've seen async programming, how we can use the primitives of async programming, async, await, join, and select, to build really complex concurrent systems. We've taken a look at some of the bugs that can happen in those systems, deadlocks and livelocks. And we've also seen a few ways in which we can resolve those, different approaches to sharing state, and also using actors. But the key takeaway that I want you to have is when you look at your code, and when you look at your code written in async await, just think about how easy it is to reason about it. It's so much easier to take the code written in async await and think about its composed parts, think about the order of operations, and then start reasoning through our concurrency bugs. And this is the really key thing that it gives us, right? It doesn't necessarily give us the same safety as tooling. It doesn't give us the safety that types and tests do. But it gives us the reassurance that we can understand our code. Now, I really encourage you to go and read more, both about async await and also about methods of thinking about concurrency. If you really like reasoning through deadlocks and livelocks, I love it, then go have a read of the little book of semaphores. It doesn't think quite in the same way, but it does have a few of these patterns inside. I'd also encourage you to take a look, even if it's just the first few chapters of CSP, Communicating Sequential Processes. This is a classic book, which is perhaps one of the seminal works almost in actors. There's, of course, the async book in Rust, so please go and have a read. Stay here as well, because there'll be tons of talks which are all about async programming. So I'm quite interested in ArcShift, looking forward to that, but also a better way of doing async Rust and embrace or ditch async. These are all going to happen later today. OK, well, thank you very much.